My name is Enrique Bello, and my research is focused on plasma oscillations in Hall effect thruster and also in other E cross B plasmas. And I'm focused right now on simulations with particle in cell codes. Okay, so I will be talking about particle in cell codes. This year I have my international stay, and I've been focused mainly on the optimization of the code that I've developed during the thesis, and also on the participation in an international benchmark to compare our results with other groups. Okay, so electric propulsion is well consolidated in the space propulsion market. We have mature technologies such as the Hall effect thruster, but mature doesn't mean that they are perfectly well understood. We are dealing with very complex plasma physics phenomena, and for that reason there is a lack of predictive numerical codes. One of the big challenges that we have is the role of turbulence, instabilities, oscillations on the electron transport, okay? And this is not only a problem of Hall effect thruster, it's a problem of other E cross B plasmas, okay? And in these kind of plasmas in which you have mutually perpendicular electric and magnetic fields, we can decompose the electron motion in different contributions. We have the gyro motion around the magnetic lines. We have the motion along the magnetic lines that is almost free. Then we have a drift in the E cross B direction. And then we have a drift in the direction of the electric field that in principle is due to collisions. However, when this electron transport in this direction is measured, the result is that it is much larger than that predicted only by collisions, so there must be other phenomena involved there, okay? And one of the main candidates is azimudal oscillations and turbulence. That is the topic of my research, okay? So this is the research outline that I've shown in previous doctoral meetings, okay? At the end, we approach this problem using different techniques, okay? Different formulations for different species. And as part of the investigation, I have developed, in collaboration with Alberto Marin, a two-dimensional axial azimudal particle in cell code to study oscillations, instabilities, etc. Okay? And this year I have the international stay in the Laplace laboratory in Toulouse, in which I've been optimizing this code, and I've been preparing the code to participate in an international benchmark. Okay, so particle in cell codes, just very briefly. The idea is to solve the Boltzmann equation for every species in the plasma, to solve for the velocity distribution function. However, we don't solve this equation directly, but we discretize the distribution function in macroparticles and solve the motion of those macroparticles instead. We need the electric and magnetic fields. In our case, the magnetic fields is given, and the electric field comes from the solution to the Poisson equation. Also, we have a module for simulating collisional processes, okay? So very briefly, this is a very general flowchart for a particle in cell code. We have the electric field in our domain, that is the input for what we call the particle loop, and for every of these particles, we have to interpolate fields to the particle positions, we have to move those particles, and we have to detect crosses with any boundaries, okay? Out of the loop, we have to simulate the interaction with those boundaries, then we have particle injection through boundaries and also volumetrically, we have the simulation of collisional operations, and then we have the volumetric weighting operation that is basically computing macroscopic properties of the plasma, for example, the densities that we need for the Poisson solver that give us the fields, okay? So this kind of simulation can be computationally very intensive. So at the end, all these codes have to be parallelized. Okay, in our case, we used OpenMP. The good thing about particles is that in every step, each particle motion is independent from the other. So this is very easily done in parallel. The parallelization of the Poisson solver is more challenging because this equation is elliptic, and due to the nature of this equation, it's very difficult to do the parallelization, okay? Apart from parallelization, there are other things that we can take into account to make our code faster, okay? For example, an efficient management of the cache memory, for example, using different compilers, different libraries, okay? Different options for OpenMP, etc. And at the end, all of these codes can become huge, can become very complex, and that is why benchmarking activities are so important, okay? Okay, so I will be commenting on some of these points, okay? I don't have time to cover all of them that I've been doing during the stay, okay? So one of the points is the parallelization of the peak code, of the particle part. We have several approaches here. We have what we call domain decomposition, in which each thread is in charge of part of the domain, okay? And the particles that are in that region of the domain. And then we have what we call particle decomposition, in which we assign directly a number of particles to each of the threads in our system. In my opinion, particle decomposition is the way to go, because domain decomposition, you have to deal with internal boundaries, you have a potential imbalance in the workload of each code, and also the implementation is generally more difficult. So we opted for particle decomposition. This is what we were doing also before the stay, but in a slightly different way, okay? Before the stay, the approach we were using is the following. We have a particle list, okay? A particle list is essentially a matrix with two indexes. The first one is the particle ID, and the second one is the state of the particle, position, velocity, etc. Okay? And what we do is to assign all these particles to different threads of our computer. Okay? But at the end, this matrix is a shared variable by all the threads in our system. Okay? And this can be problematic. Okay? Because we can have conflicts, we can have race conditions when removing or adding particles. Essentially, every time we want to access a memory location with two threads at the same time. Okay? This is also happening when we want to do the weighting operation. Okay? For example, if we are computing density, it may be the case that two threads try to update the density at one node with the contribution from two particles at the same time, and this is problematic, okay? So to avoid all these race conditions, there are several alternatives. We can do more complicated versions of the algorithms that we already have. We can use OpenMP special clauses to prevent those conflicts, or we can alternate between parallel and sequential regions in our code, but all of them come at the cost of computational cost, okay? After the stay, what I was doing was to implement a new parallelization, okay? It's, again, particle decomposition, but the idea is to avoid those race conditions without having to deal with more complicated algorithms, etc. And the idea is that instead of having just one particle list, we have one particle list per thread, okay? So each of these lists are private for each thread, and can only be updated by one thread, by the thread that they belong to, okay? So this is done by adding just a third index to the particle list matrix that is referred to the thread ID. And in this way, race conditions related with adding or removing particles are completely avoided, okay? For the weighting, we can do a similar approach. Instead of having just one density matrix, for example, we can have one matrix per thread, okay? And each thread is working or is updating the density, its own density matrix, so these race conditions are not happening. At the end, we have to add a reduction operation that in general is cheap. That is essentially adding the contribution of each thread to compute the total density, okay? And here I have some computational times as a function of the number of cores for the old version of the code, for the new version of the parallelization. And what we see is that we have a significant improvement, okay, and we have also a better scalability with the number of cores. Then we have what we call particle sorting, okay, and this has to do with the cache memory management. The main idea behind particle sorting is that those particles that are close in the domain are also close in the particle list, okay, in the matrix. Why? Because in that case, we can have some computational savings due to a more efficient use of the cache memory. Why is that? Okay, because for each of these particles, as I told you, we have to interpolate fields, we have to update the contribution of the particle to the nodes. And for that, what we need is the information in the surrounding nodes of the particle. All those values have to be loaded from the RAM memory to the cache memory. And the idea is that if we have particles in the same cell adjacent also in the particle list, those values that are already stored in the cache memory can be reused and don't have to be loaded continuously on the cache memory, and this is giving us some time savings, okay? But this sorting operation is quite expensive also, so you don't have to do it every time, okay? So in general, there is an optimum. You can do it, for example, every time steps, and if we do the sorting operation every time step, we see that the computational time for this specific simulation, okay, this is very simulation dependent, we have reduced the computational time by a factor of 2, okay? Only by doing this. Okay, just very briefly, apart from acting or developing code, there are also some computational boosts you can obtain just by testing different compilers, different libraries, okay? In our case, we were using mainly GNU compiler and math libraries, but we have for free the Intel Fortran compiler, we have the math library from Intel that can be used, and only by passing from GNU Fortran to Intel Fortran and the corresponding libraries, we observed also a significant boost in performance, okay? Not only that, but the scalability of the code with the number of threads is much better, and actually, since our workstations work with Intel processors, it makes sense that the Intel compiler works better, and actually we can take advantage from hyper-threading, okay? And finally, to end with this part, we have the options of OpenMP itself, okay, on the tool that we use to parallelize, okay? And I found that it is very important to define an affinity, okay? And affinity means to define a strategy on how OpenMP assigns the OpenMP threads in your code to your threads in your system, okay? So at the end, what I see is a significant improvement, mainly in the scalability, okay? This difference becomes bigger as the number of cores increases, between defining no affinity and defining a certain affinity, okay? I'm not going to enter into the details. Okay, and finally, I have the benchmark I was talking about, okay? It is on penny discharge type simulation, in which we have a grounded box, perfectly conducting and squared, okay? At zero potential, the walls are at zero potential. We have a uniform magnetic field that is perpendicular to the domain, and the domain is initially empty. We have an injection region here in the middle with a circular shape in which we inject certain amount of helium ions and electrons with a certain temperature following a Maxwellian distribution function, okay? And
Enrique, you have to speed up a bit.
Okay, I'm finishing. For this particular case, we consider no collisions, okay? And if we do like that, this is the evolution of the 2D map of density. We have a crazy transient, but if we wait, at the end we see the formation of a rotating structure here. This is what we call a rotating spoke, and we can measure the frequency of that spoke and compare with other groups, okay? And we obtain very similar result with a sample with the group of Princeton. Okay, and I will skip that. Another thing that we compare in the benchmark is the profiles at the intermediate section, okay? We have here profiles of electric potential, ion density, and electron temperature for several groups that so far are anonymous, but our group is this dashed line, okay? So we see that in general agrees very well with the results from other groups. Okay, I can skip the conclusion, I guess, since we are short of time. Okay, the main idea is that it is very important to know the compiler option that you have available, the libraries that you have available, because with that you can get a performance boost without having to change your code, essentially, so it is for free. Also, it is important to have proper parallelization to use completely the amount of resources that you have, and also a good management of the cache memory is important, okay? You have to be aware of that. And finally, we are very happy because the benchmark was, we think, successful, and this gives us confidence on future results obtained with this code, okay? Well, and I have here a list of achievements, journal articles, conference articles, other contributions, and that's it, okay? So if you have any question.